James Ruston, Beckham Deisha, Christopher Copeland. Our project provides an artistic toolkit for the Arts Department at MMU. This toolkit consists of a central server, a website for user interaction, a mobile application for student involvement, an image processor for effects and filtration, and a database for historical records.
The main focus of the project was to manifest data collected from sensor devices and data feeds to alter the output on a LED curtain. This was a joint project between the computing department and the art department. This was a unique collaboration. My name is Oliver Atkinson and I created the central server and the website. The server is set up of individual modules, each performing a vital role in aid of manifesting data between the website, the mobile app, the image processor, and the database. A website was developed in aid of providing a user-friendly interface for the client to be able to interact with the server easily. To gain access to the website, the client must first log in. This is a secure process. A default username and password are provided. However, additional accounts could be added. The user has now logged in. The Sensor tab provides the user with functionality to be able to interact with the sensors. A list of the available sensors is loaded from the database and are verified with the server. The sensor can be viewed in more detail by clicking on the sensor name. This action loads the sensor information from the server using Ajax, so only a portion of the screen is refreshed. The graph shown uses Ajax to refresh itself using the latest values obtained from the database. The graph is updated when the sensor value changes. An example of this is twisting the rotation sensor, as shown. Adding a new sensor is done by entering in the parameter information into the form boxes below the sensor table. The sensor types are dynamically loaded to what is connected to the Fidgets interface kit. The name and the location of the sensor are stored as strings and are used to both uniquely identify and group the sensors together. The port number is used to identify where the sensor is connected on the interface kit. Removing a sensor is as easy as going to the button on the right hand side in the sensor table. Pressing the delete button will invoke a method on the server which removes the sensor from both the server and the database. The Display tab allows the user to interact with the LED curtain displays. A script can be selected from the list. The script is assigned a main sensor before it is started. The different sensor types are loaded from the database dynamically. The user is also able to upload a script by selecting a compiled Java class file which has been created and compiled using the WYVL library provided. After the script has been successfully uploaded, the screen will automatically refresh and the script will be added to the script list. Starting a script invokes a method on the server which gets the instance of the loaded script class and instantiates it using a Java technology called reflection. Scripts have annotations stored in the header of the script. These annotations provide value-added data to the script classes such as version and author. Within the script's main method is where the computation of the sensor value and the updating of LED curtains is performed. To update the LED curtains, a request is sent to the image processor which updates the curtain using the new information. To stop a script, the user must just click stop, which will terminate the script's process. As you can see, there are multiple displays displayed on the website. And that brief overview concludes my section of the group video.
Hello, my name is James Ruston, and my part of the project was the mobile application and data feed processing. The iPhone application has a simple logo design. The loading screen is initially presented when the app is launched. While the loading screen is visible, the application fetches the data required for the app to function. Loading the data early ensures the application is free from lag. The home screen has a simple layout. The information button loads a new screen. which contains some basic information for new users. The application uses a tab bar for the main navigation. Each tab has a picture relating to the use of that tab. Clicking the Map tab loads a map displaying the location of the Chatham Tower and the location of the current user. Clicking Take Me There will launch a Google Maps app with directions to the Chatham Tower. This will be shown later in the demonstration. Clicking the Vote tab displays all the current voting entries in a table. The table shows information on the name of the entry, the name of the artist, and a small preview image of the entry. Clicking an entry brings up a full screen image of the entry with the option to vote. If vote is selected, the vote is sent to the server to be verified. Once verification is complete and the vote is registered, the user is informed. The Sensor tab loads the sensor data that is currently stored on the database. A progress bar indicates the sensor value. Clicking a sensor brings up further details about that particular sensor. A graph is also displayed to show the past sensor history. Pressing Reload gets the newest sensor data from the server. The Find button utilises the sensor data that has been collected. Users of the application can find a room that contains a sensor which exceeds a threshold value. If a room is found that matches the certain criteria, this is displayed to the user. Going back to the Map tab, when the button is clicked to get directions, the Google Maps app opens with these direction options. This concludes the demonstration of the iPhone app. The iPhone application required a way of managing voting campaigns. The website was used to provide a central access point to the whole system. A user of the system will see the current entries and the number of votes the entries have received. To delete an entry, the Delete button is pressed. The entry and associated votes are then removed from the system. To add an entry, the attributes must first be filled in. Once all details have been entered, the entry will be validated, checking the URL is valid and contains an image. Once a voting campaign is completed, the campaign can be ended by clearing all entries. A confirmation dialog is shown to ensure this cannot be achieved accidentally. The data feed processor allows for data to be collected from external data feeds. The control panel for the data feed management is contained on the main website. The website shows the data feeds that are currently being monitored on the server. Once a feed is selected, the feed messages are shown to the user. Any HTML contained in the feed is rendered in the description box. Adding a feed is dealt with very simply. Only a feed URL is required. The server then parses the feed and writes the feed details to the database. These changes are then shown to the user and confirmed. To delete a feed, the Delete button is pressed, which removes the feed from the list of feeds being monitored. The changes are, again, shown immediately using Ajax.
Hi, I'm Chris Copeland, and my area of development was the image processor for the LED displays.
I'm Chris, and I developed the imaging processing area of the project. This part of the program was written in C++ using Microsoft Visual Studio under a 64-bit Windows 7 architecture. This part was written in C++ instead of the Java platform for low-level language performance factors, since C++ is compiled directly to ASM. The speed and processing boost while using C++ is crucial for the rendering of videos and applying fast filtration algorithms such as canny edge detection. When developing the image processor, research was performed into existing libraries which could automate a lot of the functionality which was required by this engine. One library which could handle the video and webcam inputs and also provided a large array of algorithmic filters was the OpenCV library, which is favoured by both video technicians and AI developers when working with images. The second library, which was used for the rendering and visual outputs, was the engine. Highly popular for its simple class design and structure, support of many different output languages, such as OpenGL and Direct3D, and its cross-platform compatibility. Both libraries were merged together during development to combine the imaging power into a single uniform system. The purpose of the software is to visualize input data processed by the core Java application. This is managed using a network system called sockets to transfer JSON strings between both applications, with instructions on what should be displayed. This is all processed over multiple threads using mutex objects for thread safety reasons to prevent the network from slowing down or locking up the processor. The following videos feature the basics of the IMP application running to render videos and apply multiple filtration algorithms in real time. And finally, here is a small demonstration of the LED curtain display rendering images with transitions.
Hi, I'm Bekim Disha, and my part of the project was the database management system. A database management system for a data manifestation application. Why did we need a database management system after all? A database and a database management system were the overall objectives of the project. Databases and database management systems are a must-have for modern software nowadays. Important data needed to be saved, and we needed to come up with a good way to monitor the environment and provide a historical insight of events that had happened in the environment. Components of the database management system are a MySQL database for storing the data itself, a connection pool for managing connections between the database and the program, a task scheduler for scheduling cron jobs and just about any other task, an automatic logger for logging crucial and important information about the flow of the program, and a data visualizer to build graphs to visualize the data that is based in a database. MySQL was used because it was free and open source, provided entity relationship capacities, worked very well with Java, and the developer had previous experience using MySQL. MySQL was well documented and provided plenty of development examples too. PHPMyAdmin, for instance, was a free tool that was used to build the first prototypes of the database. In this image, we see a list of the tables that were used to store the data in the system. Connection pooling, on the other hand, provided better communication management, avoided concurrency issues. Connections, as we know, are expensive, and connection pooling is great for web-based applications. We had a web-based application, and providing that many users will require and try to access the database at the same time, connection pooling made the life so much easier. Connection pooling worked very well with data objects too. A task scheduler was provided by a free and open source library called Quartz from the Terracotta project. Course works well with Java, is well documented and very easy to use and develop with. A task scheduler helps our project by automatically deleting data, thus providing a window slide effect to the database, as well as triggering other jobs chronologically as required. Monitoring was used throughout the project and was implemented by implementing a log4j library that would log different operations and details about the run flow of the project straight away to the database, thus avoiding the hassle of creating so many log files. Monitoring with log4j could log just about any operation and provide it to be easy yet effective to use. This is a table of a log. Every log has a log ID, a log message of what had occurred, a log time on when that occurred, a log type, the type of a log, it could be an info, a warning, a debug, or a fatal, and a log class, providing the class where the log is coming from. This makes it so much easier for developers and users to see and witness what had happened within time. A data visualizer or a graph builder was an option that became a necessity towards the end of the project. We needed to come up with a good way to represent the data that we had in the database, and in a historical way too. Two case scenarios were studied: Google API Chart Builder or JFree-Chart. After serious consideration and after investigating the initial prototypes, Google API Chart Builder provided to do much better. Google wins. Google provided with an easy to build graph. Google provided with a good way to get the data from MySQL to build a string that will then produce an image of the graph, and all the data is coming straight away from the database. The image below shows the image produced from 5 values grabbed from the database at a range from 0 to 1000, and this shows the sensor values itself. Testing techniques were investigated and used throughout the course of the project. JUnit was a free tool to use that tests the methods and the classes of a Java program. It provided to be very reliant and very good for testing the program itself. Eclipse IDE, on the other hand, provided a debugger tool that made life so much easier in debugging the errors or the flaws of the operations in the program. On the other hand, PHPMyAdmin was used to test the entity relationship between tables and to test the database load itself.
That was a breakdown of the various sections of our final year project. We believe our prototype project has opened the door for other enterprising students in the future.
We hope you've enjoyed this demonstration and thank you for watching.